Hello, everyone. We are now moving on to Chapter 9, Gases. This is a two-weeker, so this week we will be looking at sections 1 through 3, gas pressure, relating pressure, volume, amount, and temperature, the ideal gas law, and stoichiometry of gaseous substances, mixtures, and reactions. Next week we will look at the other three sections. So, hot air balloons, here's an example of where we might see gases. They use the fact that the hot air inside the balloon is less dense than the surrounding atmospheric air, which causes them to float. So, 9.1, we are talking all about gas pressure. So, in this section, we are going to define the property of pressure, define and convert among the units of pressure measurements, describe the operation of common tools for measuring gas pressure, and calculate pressure from manometer data. So, air has been known to exist since ancient times. It's not some newfangled discovery. The Greeks considered it one of the four fundamental elements of nature, along with earth, water, and fire. And some people forget that air is a thing. And you can actually feel it, though. If you put your arms out and kind of wiggle them side to side, you're feeling that air on your hands. In the 18th century, Lavoisier, Cavendish, and Priestley determined that air is actually a mixture of gases. So our atmospheric air is not just one pure element. It's made of different gases: nitrogen, oxygen, carbon dioxide, even water vapor. So there's lots of things that go into what make up air. In contemporary issues, air is in the news a lot when it comes to, for instance, the ozone layer being depleted in the stratosphere. So we talk about the hole in the ozone layer that's been made due to things like CFCs. And then we also have the issues of carbon dioxide emissions and the contributions that those play in global warming. For me personally, I looked at air quality, and so I looked at particulate matter formation from gases reacting in the atmosphere. So I did reactions where we simulated atmospheric reactions with some gases and looked at how those could affect air quality and cloud formation. So needless to say, the gas laws and the gas chapter is very close to my heart. This is a cool little picture showing you a little bit about atmospheric pressure itself. So the atmosphere actually puts a lot of pressure on everything, on us. So 14.7 pounds of pressure. It's basically the amount of pressure that would be if you took a bowling ball and balanced it on your fingernail. But our bodies are equipped for that. We're prepared for it, and so we don't really feel that. But if you were to take a bowling ball in our current atmosphere and stick it on your finger, you're going to feel that because now you're feeling twice at the atmospheric pressure. On that note, pressure itself is the force exerted on a given area. So pressure is equal to force over area. You may have something that ends up being low pressure. Maybe that's because even though you have a very large force, it might have an even bigger area. So, for instance, let's talk about an elephant versus a skate blade pushing on to something. So, an elephant foot is 14,000 pounds. Or say it's a 14,000 pound elephant. We have 14,000 pounds for every one elephant. And each elephant has 4 feet. So we're looking at just 1 foot on the elephant. And 1 elephant foot has an area of 250 square inches. So this comes to a pressure of 14 pounds per square inch. Now let's compare this to something like the skate blade from a figure skater. Do it up here. So let's say we have a 120-pound skater. We have 120 pounds for our ice skater. And we have one ice skater for every 2 blades. And each blade has an area of 2 square inches. So the pressure that would be exerted by one of these blades is equal to 30 pounds per square inch. So it's actually more pressure from that ice skating blade that's being exerted than the elephant's foot. We could also do this for just like a human foot. So we'll use that 120 pounds person again. Okay. Times 1 skater person for 2 feet. And 1 foot has a surface area of 30 square inches. So the pressure exerted by a person's foot is about 2 pounds per square inches. And if you think about that, if you get stepped on by someone, it hurts, right? Now take that pressure and multiply it times 7 for the pressure of an elephant. Or take that pressure, multiply it times 15 for the pressure from a skate. It hurts. Another pressure thing that you can think about is backpacks. So there's some backpacks, the ones that cost a lot of money, usually have these really big kind of bulky straps on your shoulders that might have a lot of padding and are extra wide. Would you rather have that or the backpack that has strings for a strap? Most of us are going to go for that nice big wide strap, right? And that's because we know, just thinking about this, that those strings are going to dig into your shoulders, right? So that force, okay, and force depends on mass. So the more that something weighs, the more force you put on it, the more the pressure is going to be. So you have a backpack with books in it and it only has strings for the arms, it's going to hurt. So moving forward, the SI unit of pressure is the Pascal. And 1 Pascal is equal to 1 Newton per square meter. And we've looked at newtons before. That shouldn't be a 2, that should be a 1. And 1 Newton is equal to 1 kilogram meter per second squared. We looked at the newtons in chapter 8. Pascals are really, really small though. So a lot of times you'll see pressure given as a kilopascal or even as a bar. So a kilopascal, of course, is 1,000 pascals. 1 bar is equal to 100,000 pascals. The English system uses PSI, pounds per square inch. So this is one thing that you see a lot of times with tires. Usually you want your tires to be around 32 PSI. And one of the more common ways of measuring atmospheric pressure is using a mercury barometer. So this is a table in your book, table 9.1, and this gives you all these different units of pressure and how to convert. So it's really important that you're able to convert between units of pressure. It's just doing standard unit conversion that we've been doing since the very beginning. I didn't put example 9.1 in here because it's just doing unit conversion, but you can use that if you need some help. So example 9.1 if you need a little bit of extra practice. But nonetheless, you've got all these different units. The most common ones we'll probably be seeing are going to be torr, millimeters of mercury, bars, atmospheres, maybe pascals. So this is just showing you the elephant versus the ice skater. So again, back to some more units of pressure. Millimeters of mercury is a very, very commonly used unit of pressure. Sometimes there's a saying, if you're watching the news and they're talking about weather, And the forecaster says something like the mercury is rising or the mercury is falling. And this is actually talking about pressure and atmospheric pressure. And a job of a meteorologist is to relate that to weather. But the most common unit of pressure is the atmosphere, or ATM. 1 ATM is normal atmospheric pressure. So this is generally assuming sea level, just normal atmospheric pressure. For those of us that are in the high desert, the pressure is a little lower because we're higher in elevation. And 1 atmosphere is equal to 760 millimeters of mercury. So that means at normal atmospheric pressure, the measurement on a mercury barometer is 760 millimeters. We'll talk a little bit more about that in a minute. Again, the SI unit is the Pascal. We have the bar as well. 1 bar is equal to 105 pascals. We have pressure conversions here as well. So let's talk about the barometer. The barometer measures pressure in terms of the height of a column of liquid mercury. So when we say millimeters of mercury, we literally mean the height of mercury. And we'll look at a picture on the next slide. But what happens is you have some mercury that's in a container that's open to the atmosphere. And it's got an inverted like test tube type thing in it. And the atmospheric pressure pushes on the mercury, and then that pushes it into this tube. Or if the atmospheric pressure is lower, then it's going to come out of the tube into the pool. And so you measure that height in the tube to give you your pressure, and you relate that millimeters of mercury height to atmospheric pressure. The torr was initially intended to be equal to 1 millimeter of mercury. One thing we use, and we'll look at some examples with this, is hydrostatic pressure. And this is pressure exerted by a fluid due to gravity. So gravity pushing on that fluid, and that it is equal to H, so that's the height, times rho. Rho here means density. So sometimes you see a D for density, sometimes you see the rho symbol. And G here is acceleration due to gravity. So this is kind of a newer term, but it is a constant. So gravity, so G is equal to 9.81 meters per second squared. So here's a picture of a barometer. And you can also see the difference between a mercury barometer versus a water barometer. So on the left is mercury, on the right is water. Mercury, remember, is very, very dense. I believe the density is like 13.6 grams per milliliter. So you don't need much of it. So a mercury barometer is pretty small. Whereas to be able to do the same type of measurement with water, you need your column to be a lot taller. So the mercury barometer, 2.49 feet, whereas the water barometer would have to be 33.9 feet to be equal. So let's look at example 9.2, calculation of barometric pressure. So we want to show the calculation supporting the claim that atmospheric pressure near sea level corresponds to the pressure exerted by a column of mercury that is 760 millimeters high. And just reminding us, the density of mercury is 13.6 grams per cubic centimeter. So we need to use our hydrostatic pressure equation, P equals H rho G. We have an H, 760 millimeters. We know our density, and we know G. So our pressure, okay, is going to now equal where are we? Okay. So our height is 760 millimeters. So there is our height from P equals H rho G. And we're converting this to meters. And that's because we want to have the same units on either side. we want a pressure of 101,325 pascals. That's the same as the atmospheric pressure. So we go ahead and go, okay, this is a Newton per square meter, and then we're going to just change it to units that we know. So this comes down to be kilogram per meter second squared. So we need to take this millimeter height measurement and change it to meters. So that's what we're doing here. There's 1 meter per 1,000 millimeters. And then we have our density, 13.6 grams per cubic centimeter. And we need to get this to be kilograms and meters. So we know there's 1 kilogram per 1,000 grams. So there's our grams canceling. And then we have 100 centimeters for every 1 meter, and we have to cube it to get rid of the cubic centimeters. And then lastly, our G is in the correct units already. We're good. So when we put everything together, we get 1.01 times 10 to the 5th Newton per square meter. And that is right about the exact same number. So we're showing, yes, this is accurate. This is atmospheric pressure. So atmospheric pressure itself varies with the height of the column of air that's above it. So we don't notice atmospheric pressure itself, but we do notice change in it. So for instance, if you're in an airplane at a higher elevation, or if you're just driving up and down the hill, your ears may pop, and that's because there's a difference in pressure. Oftentimes, if you're looking at directions for like cooking pasta, it even has information on what to do at higher elevations, because the pressure can change the boiling point and freezing point of matter. And we'll talk about that probably later. So now we're going to talk about the manometer. We looked at a barometer, now we're going to talk about the manometer. And this uses a force of gas. It's in a flask that's measured relative to the force of the atmosphere. So we look at the direction that the mercury in it travels, and we are able to relate that to the pressure of the gas. So we have these different types. We have a closed end manometer and an open end. And again, this is for measuring the pressure of a gas, not necessarily the pressure of the atmosphere. So we have some gas here. And in a closed end manometer, when we let our gas flow, it's going to push the mercury here up until it stops and is equalized. And the distance that the mercury travels, so this height here from where the gas stops the mercury to where the mercury itself stops, this height is our height in our equation. So for a closed-end vacuum manometer, the pressure of our gas is equal to that H rho G equation. Now, if we have an open-end manometer, and we open our gas up and it pushes our mercury, and we notice that the mercury on the gas side is higher than the mercury on the open end, then our pressure of our gas is equal to our atmospheric pressure minus H rho G. So the atmospheric pressure minus this difference. If you notice that the mercury on the gas side is lower than the mercury on the open end, then our gas pressure is the atmospheric pressure plus H rho G. So this is how we use a manometer to get the pressure of a gas. So we're going to look at a couple examples. This first one, we want to figure out the pressure of this gas in torr, pascals, and in bar. So we are given a height here, 26.4 centimeters. And we notice this is a closed end manometer, so that means that our pressure is equal to H rho G. So we have an H. We are using mercury, so that means our density is 13.6 grams per cubic centimeter. And our G is 9.81 grams, or not kilograms, sorry. Meters per second squared. So this is a matter of converting units and plugging and chugging. So if we start here, we have 26.4 centimeters. We're going to start with the torr measurement. And we are first going to go make this guy. Oh, actually, there's an easier way to do it. Well, you can use the P equals H rho G. Perfectly fine. But the other way you can do it, and I was totally overthinking this, is you can convert the centimeters of mercury to millimeters of mercury. And now you have a regular unit of pressure, and then you can convert that straight to torr. And then from torr to pascals, and from pascals to bar. So it's even easier than I was thinking. So we take our centimeters of mercury, 26.4, change it to millimeters of mercury. There's 10 millimeters per 1 centimeter. And then we know there's 1 torr per millimeter of mercury. So we have 264 torr. And now we can go ahead and convert from torr to pascals. 264 torr, and we know there's 1 ATM for every 760 torr. And then there are 101,325 pascals per 1 ATM, gives us 35,200 pascals. And lastly, we need to go to bars. 35,200 pascals times 1 bar per 100,000 pascals gives us 0.352 bar. So you can do it that way as well, and that's probably the easier, quicker way to do it. The next one is using an open-end manometer. So we've got our height, and we have a mercury manometer. So we know we have an H of 13.7 centimeters. We have a density of 13.6 grams per cubic centimeter. And acceleration due to gravity of 9.81 meters per second squared. And we want to get our pressure in millimeters of mercury, ATM, and kilopascal. Now, with an open end, we can't just do changing our centimeters of mercury to millimeters, because we have to take into account that pressure from the atmosphere. So we need to take in hydrostatic pressure. And we see that the mercury is higher than the gas level. So that means that our pressures are going to add. So our pressure of our gas is equal to our atmospheric pressure plus H rho G. So we can go ahead and just change this 13.7 centimeters to millimeters of mercury. That's going to be the H rho G in this version. Okay. So we can still kind of use that little trick there. And then we're going to add that to the atmospheric pressure, which is 760 millimeters of mercury. And we get 897 millimeters of mercury. And we can go ahead and use that and convert now to the other types of pressure. Once you have one of the pressures, you can convert it to the others. You don't have to do the same calculation over and over. Just another type of pressure monitor is blood pressure. We have a sphygmomanometer. I don't know if I said that right or not. I probably did not. Sphygmomanometer. I'm not a medical professional. Meteorologists use weather maps to describe and predict weather. So they talk about high and low pressure, talk about, oh, the mercury is rising today, yada, yada. That's another example of where you might see pressure. And then Earth's atmosphere. So for those of us that are atmospheric scientists and engineers, my work that I studied was focusing on effects on the troposphere. So our atmosphere itself, the lower atmosphere. There's lots of work done on the stratosphere, mesosphere, not so much in the thermosphere and exosphere, but these are the other layers of the atmosphere.